In the first sequence, we begin with 100 bacteria that are initially located at the origin and then follow the paths traced by their motion. This is done in the presence of a linear attractant gradient, which increases from left to right in the positive z direction. Then we jump ahead to 30 seconds of elapsed time, as indicated by the clock in the upper right-hand corner. Note that the run lengths toward the right are longer on average than those to the left, which creates an asymmetrical pattern on the screen. Changes in direction occur more frequently for bacteria moving toward the left. Periodically, we restart the trails in order to speed up the subsequent calculations. Now we will rotate the simulation box from the YZ plane to the YX plane. In the YX plane, the attractant concentration is uniform. In the absence of concentration gradients, the bacteria exhibit what is called random motility. The run lengths have the same distribution regardless of their direction. The pattern traced out by the bacterial population is symmetrical and resembles the random walk behavior analogous to molecular diffusion. Finally, we've rotated back to the YZ plane and see the pattern due to chemotaxis after an elapsed time of 1 minute and 15 seconds. In the second sequence, only the current position of the bacteria is shown. Here we started with bacteria randomly distributed within the simulation box and have applied periodic boundary conditions. In other words, for every bacterium leaving the right-hand side of the box, another will enter at the same location on the left-hand side, and similarly for the top and bottom and back and front. With these boundary conditions, we are able to maintain the same number of bacteria within the simulation box at all times. Again, an attractant gradient has been imposed in the positive z direction from left to right. If you follow a bacterium moving to the right, it should change direction less frequently on average than one moving toward the left. By rotating the box back to the YX plane, we can observe random motility in the absence of a chemical gradient. Now a bacterium moving toward the right should change direction just as often as a bacterium moving toward the left. The following segment shows the random motility of an actual bacterial population which we captured by video microscopy. The swimming behavior of Escherichia coli were taped in real time at a magnification of 1250x. The bacteria are 1 to 2 microns in length and swim at speeds of 20 to 40 microns per second. This corresponds to about 10 to 20 body lengths per second. If you follow an individual bacterium, you will observe the characteristic pattern of runs and tumbles which we saw previously in the simulations. However, changes in direction do appear to be somewhat more gradual than those in the simulation. Because we are restricted by the depth of field to essentially 2 dimensions, bacteria will move in and out of focus when they are swimming in the 3rd dimension. Note that many of the bacteria appear to be non-modal. This is because we are focusing just below the cover slip, and a number of the bacteria have attached themselves to the cover slip surface. If we focused further into the liquid media away from the cover slip, we'd see about 95% of the bacteria in motion. In the 4th sequence, we simulate the experimental conditions in the stop flow diffusion chamber. Initially, the bacteria are uniformly distributed within the simulation box, and a step change in the attractant concentration is imposed in the z direction. The red line represents the change in concentration profile. As we move ahead in time, notice the formation of light and dark bands near the center of the simulation box. These bands represent regions of high and low bacterial density from the chemotactic response. As the simulation box is rotated to the YX plane, we can see that the bacterial density remains uniform in the absence of a chemical gradient. The bacterial density profile in the z direction is shown in the upper left-hand corner of the screen, so we can continue to follow the development of the bacterial density profile as the attractant gradient changes. Finally, we rotate back to the ZX plane. In the final sequence, we have increased the number of bacteria in the box tenfold in order to correspond to bacterial densities typically used in experiments. This makes visualization of the light and dark bands easier, but does slow the computations. If we jump ahead in time and show the results near 2 minutes, the high density and low density bands are quite evident, and they closely resemble what is observed experimentally in the stop flow diffusion chamber. Finally, at 4 minutes, note that the bands have moved toward higher attractant concentrations in the bottom of the chamber and have broadened with time due to the random motility component of population migration.